Hi, my name is Nicholas Yu, and I'm a chemical engineering senior. Today I'll be presenting my research project titled The Atomic Scale Interaction Between Nanomaterials and Polymers. First off, I'd like to thank Dr. Bo Lee, who is my faculty head, Dr. Kai Zhao in the Oak Ridge National Laboratory for sponsoring part of our research at their esteemed lab, and of course the Falvey Memorial Library. For a quick background, you may be wondering what nanomaterials even are. And nanomaterials are materials that are about an atom layer thick. Typically, they have high electrical conductivity and mechanical strength, which gives them a wide variety of applications in fields ranging from energy to aviation and space. We decided to use molybdenum diselenide, or MLSE2 for short, in our research project because we had done previous experiments on the material that yielded evidence that defects in its crystalline structure controlled the assembly of polyethylene on its surface. And so the purpose of our project was to investigate this interaction between the polymer and the nanomaterial at the atomic level, because we have found that there's no previous research done at the atomic scale of this interaction. And this research could lead to new insights on how to control the properties of nanomaterials and their polymer composites. And this finer control of their properties would make these materials even more useful in its wide variety of applications. The Falvey Memorial Library was very helpful through our entire project because it helped us develop our own highly controllable solution-based method for assembling PE on MLSE2. And it also allowed us to investigate the properties of pure MLSE2 and compare our experimental results with that of previous research. And so our methods used to synthesize MLSE2 was a basic chemical vapor deposition method, which will be explained in the next slide. And to synthesize the polymer nanomaterial composite, polyethylene was first dissolved in xylene at about 130 degrees C, then transferred to a cooler oil bath, which ranged from temperatures of 90 to 125 degrees C. And at this recrystallization oil bath, at the cooler temperature, a silicon chip with a CVD-grown MLSE2 was inserted into a solution for varying amounts of time to control its growth. And so the chemical vapor deposition is shown here, where the pure materials of selenide and molybdenum are put into this vacuum sealed tube at high temperatures, and then hydrogen and argon vapor is shot through the tube to deposit the selenide on the molybdenum and synthesize our MLSE2. A diagram of our solution-based assembly is displayed here as well, where these polymer chains are dissolved and dispersed in the xylene solution. And as it recrystallizes, it'll assemble on our molybdenum selenide surface and give us our composite structure. Initially, what we wanted to see was if the polymer deposited epitaxially on the nanomaterial surface. What that means is that the polymer deposits purely on the surface and has no interactions below it. And using Falvey's databases and resources, we were able to check the Raman and PL peaks of pure MLSE2. And we found that no matter what growth temperature, no matter how high the polymer were, all the peaks remain about the same, which was exactly what we wanted to see, because it meant that there's no shifting of peaks and the polymer wasn't interacting below the surface level. And here are optical and SEM images of the MLSE2 and the composite material. As you can see in the bottom right corner image, the PE lamella grow in specific structures on the MLSE2 surface, which we would later find would be because of different defects in the crystalline structure. As displayed here, there's a grain boundary in the top right image, which goes horizontally across the image, and the polymers seem to grow outwards from the grain boundary. And what a grain boundary is that in a crystalline structure, you won't get all perfect crystal. You'll have grains of crystal that will grow against each other and form these grain boundaries as it's all not one perfect structure. There's also different defects that we found controlled the growth of the polymer structure. For example, there's edge defects where at the very edge, the polymer seems to grow perpendicularly to it. And then in lateral edges and the layer edges, there are also patterns of growth for the polymer to grow out of, as displayed in the bottom right corner, where it seems the polymers are growing out from the edge and then in a triangle out from the center. We also found that different growth times would affect the height of the polymer structures. So as you can see here in the bottom right image, the height of the P lamella was highly affected by the time and temperature of the growth procedure. So we found that 90 degrees Celsius achieved the highest growth times, and as the time went on, there was this sharp growth and then a kind of a plateauing off. And as the temperatures got higher, there was even less and less polymer growing on it. We found that 90 degrees Celsius was the best growth temperature, and the assembly time would dictate how high you wanted the polymer to grow. And these other images are just displaying exactly what the image looked like. There's the line profile, which just demonstrates the kind of rough structure of the lamella going up and down. And yeah, we found that the height was highly controllable with temperature and the time. So in conclusion, we've managed to develop a highly efficient and accurate solution-based assembly of an inorganic and organic hybrid structures, or of the polymer and the nanomaterial structures. And we found that the defects in the nanomaterial crystalline structure effectively controlled the nanomaterial polymer interaction, as you could see with the way the polymer growed out from the defects. And so this could lead to a lot of different applications and further use for these hybrid materials. Thank you all for listening.
Thank you, Nick. So does anybody have any questions? And again, to kick it off, I'd like to ask, what were the particular challenges or surprises from all of the experimentation that you did for this project?
Initially, there were a lot of challenges because I was kind of coming into this research not knowing anything at all about any of the analytic techniques we were using, not much about like the polymer growth and everything like that. So that's where Falvey Library actually came in a lot of help, because I was able to use their resources and databases, look up all the information I needed. For example, like the Raman and PL spectroscopy that we did, those graphs, I had zero clue what those were coming into doing this research. But after researching it and going into it, I managed to come out with a pretty good understanding of how to use it and like what it actually does and everything like that. So initially, there's a lot of challenge and struggle, but I managed to figure it out along the way, and yeah.
Okay, we had another question come in about how are you able to get those images?
So there's optical images and scanning electron microscopy images and AFM images. So I'll go through all of them as I go along. So optical images are pretty simple. They're just like basic cameras that are zoomed way in. The scale on these is like micrometers and nanometers, so really small. So optical images is just basic light, and SEM is short for scanning electron microscopy. Essentially what that is, they send an electron beam onto your sample, and then based on how conductive the sample is and stuff like that, it'll send like an electrical signal back, and then you'll be able to see the pattern of what's going on with the pattern of electrons that bounce off. And then for AFM, it's called atomic force microscopy. That uses also a high definition camera, very zoomed in, but it also uses this needle that kind of goes across the surface of your sample that will go up and down based on the height. And since it's like nanometers and micrometers kind of resolution, it's obviously a very fine needle that goes across. And so you can kind of map out specific structures of your sample using that. And so that's how I got those images.
We have another question about polymer growth is optimal at 90 degrees C. So how stable is the polymer at lower and higher temperatures?
So 90 degrees C was actually the lowest temperature we used, because initially we thought the recrystallization temperature for the polymer was around 100 to 125. But at 125, we didn't get any polymer growth pretty much at all. And then 120, same. And we only really saw anything around 100 degrees Celsius. And so we're thinking, that's kind of weird. We thought that's like what our recrystallization temperature was. And so we just tried 9 degrees Celsius to like see what would happen. We saw this huge growth. And when we saw that, we were like, we actually don't want it to be any higher than this after maximum time. So we figured we'd stop at 9 degrees Celsius and go from there.
You mentioned at the end of your presentation that there's lots of potential applications for this research. So can you just mention a few of those?
Yeah, so the big one we were looking at was flexible electronics. So potentially things that are biocompatible, stuff like maybe a heartbeat sensor that will like wrap around your skin, that will like blend right in, stuff like that. And the thing about nanomaterials is that there's such a wide variety of applications depending on how you synthesize them, what you do with them, and everything like that. So the main thing we're focusing on was looking at flexible electronics, but this could go into like anything electrical because MLSE2 specifically is really great in transistors, which is pretty much in every consumer electronic, every electronic device you can think of. So yeah.
So thank you very much, Nick. We're actually going to now take a 5-minute break to allow our schedule to get a little back on schedule. So everybody feel free to get yourself a glass of water and we'll come back at 9:37.